Okay, so we're now going to look at electric fields, which is on page 210 of your textbook, so make sure you got it with you. Alright, and we're going to go through it fairly quickly. So we've done electrostatic forces, so we just need to remember a couple of things. So first of all, an electric field is a region in space in which an electric charge experiences a force. So it's a region in space. You've seen something similar to this when you did magnetic fields. Okay, so an electric field is like a magnetic field, but it's created by an electric charge. Okay, and another electric charge can feel and experience that electric field. So how do we represent electric fields? Well, we use field lines, which are just a way of representing an electric field. Okay, so it's just the way we represent it. And what are those properties? Well, number 1 and 2, they're imaginary. You can't see them, they don't exist. We draw them as lines, but actually the field is continuous. They always, so this is an important one here, they always point away from a positive charge and towards a negative. That's a convention. So all scientists use the same thing there. They never, ever, ever cross, just like magnetic fields that you did in grade 10. They start and end perpendicular to the surface, and they indicate a strong field. So a strong field means they must be close together, and a weak field, oops, I've run out of space over here, weak field must be far apart. So how close they are tells you how strong the electric field is, okay? And that would then be either because of the distance from the electric field or because of the size of the charge, okay? That means we get to the shape of the electric field. So the first one is when we have a positive charge. Now remember, we said it's away from a positive, so it's got to go away from the positive because this is a positive charge. It must touch over there, and what we were saying just now, here, that part of the electric field is much stronger than this part of the electric field, because over here, the lines are closer together, over here, they're further apart. For the negative charge, the shape looks exactly the same, okay? The difference being that now it points towards the negative. This direction is very important. You must learn this, okay? Must be not, please draw it with a ruler. You make sure that your lines don't cross. You make sure they're nicely spread out, okay? Now, when we have 2-point charges, you know from previous year's work that like charges repel and unlike charges attract. Now, with like charges, when they come together, what's really important is they can't cross. So this has got to be an empty space here. There can't be any fields over there. Okay, now these are pointing away because we have positive charges over here. If these had been 2 negative charges, the only difference would be that the direction changes. It would look exactly the same. You don't have to draw as many lines as this is in an exam, but you have to draw the same number on both sides because your exams only have, they have specified that you'll have the same charges on both of these, okay? So both charges have to be the same value. Then when we look at unlike charges, which you know attract, and if you look carefully, the middle looks a little like the field around a magnet. So it goes from the positive to the negative, okay? And that's a straight line. It looks a little like a little spider or some sort of funny insect. And once again, you've got to make sure that you have the same number of lines on both of them, because even though one's negative and one's positive, their magnitude will be the same. They'll have the same charge, same value of charge, even if they're different signs, okay? And how many lines you have represents the value of the charge. So that gets us to electric field strength. This is a vector. This is a brand new concept for you. Now, the electric field strength at a point, okay, is the electrostatic force experienced per unit positive charge. This per unit positive charge, that positive charge is considered a test charge, okay? So we use it as a test charge, and it's a convention, okay? It is completely and utterly a convention. It's nothing else than that, okay? It's just what scientists decided. So we're going to talk about the forces in the electric field, because I mentioned electrostatic force per unit charge. That gets us to our first equation, where E equals F over Q. Now be careful here. This is the only section where Q can be both a capital and a lowercase, okay? And it's quite nice that this is a lowercase, because E is equal to the electric field strength, new unit for you, which is newtons, which is what force is measured per coulomb. That's where it comes from. Force is F, which is experienced, and then we get this. The charge is, Q is the charge experienced in the field. So what I'm saying to you is this, is if I have an electric field, so this is an electric field, we don't care how it's being created, okay, it's got a direction, and over here I put a little Q, okay, this is the Q that's in here, this is the electric field. This Q is going to experience a force because of the electric field, so it's got to be the one experiencing it. Okay, it's not making the field, it's experiencing the field. Like, you don't make the Earth's gravitational field, but you definitely experience the Earth's gravitational field. So, example, we have a charge. All right, now I've done it in color for a reason. 4,5 nanocoulombs. So we remember what, actually I can't use that in nanocoulombs, so that's times 10 to the minus 9. It's placed in an electric field, so it's placed in an electric field, that means that's little q, where the field strength is 4,5 times 10 to the 5, 4 times 10 to the 5 Newton per coulomb. What is the magnitude? So they're not looking for a direction of the force. And in fact, we don't have enough information to give you direction. So, what do we know? E is 4 times 10 to the 5. Make a note here, please, guys. E is always very big. Always very big. Okay? Q is always very small. And I've already done the conversion. And so is F. F's also going to be very small. So we look at this and we go, well, actually, I've got E, I've got Q, I want F. I'm going to use E equals F over Q. I do my straightforward substitution. Getting the answer for F is a maths problem. I don't need direction because the question asked for magnitude. Okay, so there's my answer. Done. Let's look at another example. A charge experiences a force of 2,8 times 10 to the minus 3. So that's F. When placed in an electric field at a point where the strength of the field, so that's E, is 7 times 10 to the 5. What is the magnitude of the charge? Once again, I don't have enough information to say whether this charge is positive or negative. So E equals 7 times 10 to the 5. Q is what we're looking for, and we know F is 2,8 times 10 to the minus 3. Great. So E equals F over Q, 7,5. 7 times 10 to the 5 is equal to 2,8 times 10 to the minus 3. So we solve for Q. It's nice and small. Straightforward. I can't at this point say that it's positive or negative. I'd need more information, like a diagram, or they'd have to say something about direction. This is not enough. Okay? So, this is for the charge that's experienced in the field. But we don't actually have to have a charge in an electric field. Charges make electric fields. So now how do we work out those? Well, if I have a big Q inside an electric field, and there's R, okay, I know there's the strength of the electric field at a certain point. It's a new equation, E equals KQ of R squared. It looks a little like F equals KQ of R, KQ1, Q2 of R squared. Please be careful here. It's amazing how many of you will substitute an F here instead of an E, or put an E in front of the Coulomb's law equation when you shouldn't. So, E is electric field strength. That hasn't changed. K is our constant, 9 times 10 to the 9. Q is now the charge making the field. That's why it's a big Q. It's like the Earth making the gravitational field. R is the distance from Q. So, example. Calculate the electric field 30 millimeters away from a plus 2 microcoulomb charge. So that's R, that's then Q. That's really why we need to always put in well, it's always good to make a list, because it makes it easy for us to decide which equation goes with what equation we're using. So E is what we're looking for, electric field. Q is plus 2 microcoulombs, which means it's 2 times 10 to the minus 6 coulombs. And R is 30 millimeters or 0.03 meters. So, E equals KQ over R squared. Straightforward substitution, 9 times 10 to the 9, 2 times 10 to the minus 3, and 0.03 squared. Please don't forget out that square, which gives us 2 times 10 to the 7. Now, how did I know that it was away? Because that's a positive charge, okay? Remember, our electric field goes away from a positive and towards a negative. I can't put left, right, up, down. I don't know which direction from the charge I went. So away is fine. It's going away from my charge. All right. Net electric field. Now, before the wheels fall off. Net electric field, listen to this, says, are calculated in the same way as net force with a vector calculation. Same as what we did with net force, we calculate each of the fields that we're looking for and then look for net. So here we have example 2. The diagram shows Q1 over here, which is plus 0.05 microcoulombs, and we have minus 0.4 microcoulombs, and they say calculate the electric field strength at A. A is not a charge, it is a point. So what we do here is we now go, well, what is E at A because of Q1? What is E at A because of Q3? You're very rarely going to use E equals F over Q in this equation, but you might. Just look at what you've got. So, this is a positive charge, so the field points in that direction. It's going to go to the right because it's away from the positive. This is a negative charge, so the field points towards it. Now, this is quite nice. So, when I look at it, there's my point. The electric field on A, at A because of Q1 is to the right, and the electric field at A because of EQ3 is to the right. That's nice. That means I just need to add them together. So the first thing we do is we work out each one separately. This 0.1 is actually fairly straightforward because if you look at it, it's 100 millimeters. Okay, so that means that's 0.1 meters. This is 80, 0.08 millimeters. Straightforward substitution. Now we do the same with Q3. It's also to the right, which then means when we can add the two together, we don't have to minus any. Don't forget direction at the end. Okay, so now you need to look at the activity on page 215, questions 1 to 5, and the memos will be put onto Teams for you. Okay.